So, in the last lecture we were solving unsteady problems in unidirectional transport in a Cartesian coordinate system. Okay. So, the scaled temperature field satisfied the equation partial T by partial T is equal to d square T by dz square, and we had certain boundary conditions and initial conditions, and we were solving in a Cartesian coordinate system. Okay. So, the first configuration that we chose was between z star is equal to 0, z star is equal to 1. Here T star was equal to 1, and at the top surface T star was equal to 0. And the steady solution was a linear function. Okay. This was the steady solution. Oh, sorry, Ts. The steady solution that is independent of time. Okay. That goes from T star is equal to 1 at this point to T star is equal to 0 at this point. And we were solving for the transient part. Okay. The transient part had the same dependence, had the same differential equation as the steady solution, except that at boundaries this transient part was equal to 0. Okay. That was homogeneous boundary conditions. Okay. We had applied homogeneous boundary conditions for the transient part at the boundaries. Okay. The other problem that we had solved was two slabs being brought together. Okay. The steady solution in this case was just a constant temperature. Okay. T star is equal to 0. Okay. And I had insulating surfaces at the top and bottom. So, the heat flux is 0. The steady solution was this, and the initial temperature profile looks something like this. Okay. The steady solution was T star is equal to 0. The initial profile was T star is equal to 1 here and T star is equal to minus 1 here. And here the z coordinate was z star is equal to 0, z star equals 1, z star equals minus 1 at the bottom. So, those were the temperature profiles initially and in the final steady state. And in this particular case, at boundaries, okay, I had partial T by partial Z is equal to 0, and I had also told you that these are also homogeneous boundary conditions. Okay. I told you that these are also homogeneous boundary conditions. And then we had got solutions, okay, of the form. Okay. In this case, for the transient temperature profile, I had summation of ai sine of I pi z e power minus I pi the whole square t. Okay. In this case, I was equal to 1 to infinity because the sine function was 0 at 0. Okay. So, In this case, I had got for the transient part summation of a I sine of 2n plus 1 I pi z by 2 e power minus 2n plus 1 I sorry 2 I plus 1 pi z by 2, and over here I have 2 I plus 1 pi by 2 the whole square t. Okay, t has to be down. Exponential in both cases in time, and sine functions or cosine functions in the spatial coordinates. Okay. And I had derived specifically for these two different cases for you that both of these functions satisfy what is called the orthogonality relation, that sine of I pi z times sine of j pi z from 0 to 1 is non-zero only if I is equal to j. It is equal to 0 if I is not equal to j. Okay. Similarly, in that case as well, integral from minus 1 to 1 of sine of 2 I plus 1 pi z by 2 times sine of 2 j plus 1 psi z by 2, that was 0 if I was not equal to j, and that was non-zero only if I is equal to j. There is a square here, please note that there is a mistake there, it should be the square. Okay. So, in both of these cases there is a common form for t. Okay. A I times some function of beta I z e power minus beta I square t. That is the common form of the function in both of these cases. Okay. Where this function psi satisfies the homogeneous boundary conditions, either psi is equal to 0 or d psi by dz is equal to 0. And I told you that if the solution of this is of this form, where this function psi satisfies the homogeneous boundary conditions, then these functions are orthogonal. Okay. The function for beta I multiplied by the function for beta j integrated over z from 0 to 1 has to be 0 if I is not equal to j. It appeared when we solved it for those specific cases that it was actually a coincidence, that in this particular case coincidentally these two functions turned out to be orthogonal to each other. Okay. Turns out that that is not the case. Okay. You can show that these functions are always orthogonal provided the boundary conditions are homogeneous. And it is for that reason that I had emphasized while doing separation of variables, we have to reduce the problem to a form where the boundary conditions are homogeneous. Okay. So, let us take a function, okay, which satisfies this condition, okay, d square psi of beta I z by dz square is equal to minus beta I square psi. Okay. Okay. Let us take a function of this type. Okay. And similarly, for some other integer j, you will get d square psi of beta j z by dz square is equal to minus beta j square psi of okay. So, for I you get minus beta I square, for j you get minus beta j square, and you can see that these sine functions, so these two functions are actually functions that satisfy that particular form, okay, in a Cartesian coordinate system. Okay. So, these functions actually satisfy this particular form in a Cartesian coordinate system. Okay. Now, if I apply boundary conditions, I can have psi of beta I z is equal to 0, okay, or d psi by dz is equal to 0. Either the function can be 0 or its derivative can be 0. Okay. Or you could even have something of the form psi of beta I z is equal to some constant times d psi of beta I z by dz. Okay. You could even have it in this mixed form. Okay. These are all homogeneous boundary conditions. Okay. So, if I have this homogeneous boundary condition, right, then I would like to know what is the integral. Okay. I would know what is like to know what is the integral dz between the boundaries. Okay. So, this is the boundary condition. Okay. One of these boundary conditions has to be satisfied at both boundaries, which I will call z star is equal to 0 to 1 for simplicity. Okay. I can always scale it in such a way that the boundary goes from 0 to 1. Okay. Okay. What is this? Okay. This, okay, what I will call the inner product. Okay. Okay. Or scalar product. Okay. What is this given by? Okay. So, we get it by a slightly roundabout derivation. So, let me go through that. Okay. If I take integral, okay, 0 to 1 dz star, okay, of psi of beta I z star d square okay. Consider this integral. Okay. We know that this second derivative has to satisfy this equation. Okay. The second derivative has to satisfy this equation. Therefore, I can write it in one way as minus beta j square, right, integral dz star okay. So, that is one way of writing it. Okay. I label this as 1. Okay. I could also evaluate the left side by integrating it by parts. Okay. By integrating the left side by parts, because I have a second derivative of psi of beta jz. Okay. So, I could integrate by parts. Okay. So, the first I will get this is equal to psi of beta j z star d I am sorry, the first term has to be psi of beta I z star d psi of beta j z star by dz star, okay, between 0 and 1. Okay. Integration by parts. I first write this as this minus integral 0 to 1 dz star, okay, of d psi of beta I z star by dz star okay. So, I have used one integration by parts to transfer one derivative from the second function to the first function, okay. And then I use another integration by parts to transfer the second derivative as well, okay. So, I will get okay, minus okay. So, I am transferring the second derivative, okay, the second derivative here from the second term to the first term by integration by parts, okay. I am transferring the second derivative, okay. So, I will get minus psi of beta j z star d psi of okay, between 0 and 1, okay, plus, okay, integral dz star okay, between 0 and 1 of d square psi of beta I z and this term here, okay, this term, the second term here, this is just equal to minus beta I square, okay. This is just equal to minus beta I square times psi of beta I z star, okay. So, therefore, I will get the first two terms as usual, minus beta I square times integral 0 to 1 dz times okay. Note that this term here, this number 1, okay, which we had here, minus beta j square into this is equal to this entire thing, okay, is equal to this entire thing, because these were just two different ways of simplifying this same initial expression. The first one by just substituting beta square times psi for d square psi by dz square, okay. The second one used integration by parts, okay. So, these two are equal, okay. So, these two are equal, okay. So, therefore, I get, okay, you can see that I can take this second term on the right to the left hand side, okay, and I will get beta I square minus beta j square integral 0 to 1 okay, is equal to this right hand side here, okay, which is both of these are evaluated at 0 and 1. Okay. Both of these are the boundary terms. Okay. I got those by integration by parts. So, they have to be evaluated at the two limits, okay, is equal to this thing evaluated, okay, this whole thing has to be evaluated at the two limits 0 and 1. So, this is what I get for this integral. You take two terms, the inner product or the scalar product that I talked about. If you take the product of two functions, integral from 0 to 1, it has to satisfy this relation. Examine the terms on the right. Okay. If psi is equal to 0 on both boundaries, then that is identical to 0. The right side is identically 0. If the derivative is 0 on both boundaries, then the right side is also identically 0. Okay. If psi is 0 on one boundary and the derivative is 0 on the other boundary, then also it is equal to 0. Okay. And if I have a relationship between the values at the boundaries of this form, okay, if I have a relationship between the values of the boundaries at this form, you can easily substitute that into this equation and you will see that the right side is also equal to 0. Okay. So, whenever beta I square minus beta j square is non-zero, okay, whenever this product is non-zero, right, the right side is equal to 0, okay, which means that this is equal to integral has to be equal to 0 for I is not equal to j, okay, because if I is not equal to j and beta I is not equal to beta j, I can divide the right side by beta I square minus beta j square, and once I do that I will get that this integral 0 to 1 dz psi of beta I z psi of beta j z. This has to be equal to 0 for I is not equal to j. Okay. This has to be 0 for I is not equal to j. Okay. If I is equal to j, then the left side is also 0. Okay. So, therefore, the integral cannot be 0. In fact, if I is equal to j, you are integrating the square of a number and the square of a number is always positive. Okay. So, you have to get a non-zero value. Okay. However, if I is not equal to j, that means that the right side has to be equal to 0. That means that these functions are orthogonal, that is, if you take the inner product of these functions, inner product defined as the integral over the domain of psi of beta I z and psi of beta j z, integrated over the domain, that has to be equal to 0 provided the boundary conditions are homogeneous. And if that is equal to 0, right, if that is equal to 0, then the solution that I had here, okay, the solution that I had here was T star is equal to summation of A I psi of beta I t e power minus beta I square t. Okay. At t equal to 0, we have the initial condition. Okay. T star is equal to sum f naught of t. Okay. We had the initial condition that T star is equal to some function of t. Okay. This implies that at t is equal to 0, this summation of A I psi of beta I t is equal to f naught of, we call that as, okay, some T star naught. Okay. T star naught is the, this is in general a function of z. Okay. At initial time, the temperature distribution is a function of z. Okay. So, if I have this, then this becomes T star naught of z. Okay. And this in general I is equal to 0 to infinity. Okay. So, I have this as the initial condition. Okay. In order to determine the coefficients, since I have this orthogonality relation, only if the conditions, boundary conditions are homogeneous, only if the boundary conditions are homogeneous and the psi satisfies the boundary condition on both boundaries, then I have this orthogonality relation. Therefore, I can multiply both sides by psi of and integrate from 0 to 1. This I will get it as 0 to 1 dz star, that initial distribution, which depends upon z, times psi of beta j z. And on the left side I am guaranteed that this is some constant times delta I j, because it is 0 unless I is equal to j. So, on the left side I always get I is equal to 0 to infinity a I delta I j times some constant j. That constant was 1/2 for the first problem that we solved, it was 1 for the second problem. So, we are guaranteed that this solution exists, and since the summation is over all I and delta I j is non-zero only when I is equal to j, I get A j times C j. Where T naught is the initial distribution at time t is equal to 0. The initial distribution at time t is equal to 0. And because of this, we can evaluate each coefficient individually because of this orthogonality relation. The orthogonality relation is valid because the function satisfies homogeneous boundary conditions, and therefore, the right side of this equation is equal to 0. So, if you have homogeneous boundary conditions and this operator, the second derivative operator, then you are guaranteed that if the conditions, boundary conditions are homogeneous, then the functions, the solutions for different integer values of I are orthogonal to each other or perpendicular to each other, and therefore, if you multiply two different functions and integrate, you will get 0. And you can use that orthogonality condition in order to solve for these coefficients A I. And in that way, you get explicit solutions for these functions A I. So, this is the rationale why we could use orthogonality relations in both of the problems that we had solved. It is not a coincidence that when I multiplied it by another function and integrated, I got 0. The reason is because the boundary conditions are homogeneous, and it is what is called an eigenvalue problem. This beta I and beta j are what are called eigenvalues, and because it is an eigenvalue problem and the boundary conditions are homogeneous, I am guaranteed that the orthogonality relation holds, and because the orthogonality relation holds, I can explicitly determine all the coefficients in the expansion. And that is the reason I had emphasized that we have to make sure the boundary conditions are homogeneous in the spatial directions for the time dependent problem, the unsteady, the transient part of the solution. We have to make sure that the boundary conditions are homogeneous. So, this completes our discussion of separation of variables in a Cartesian coordinate system. We will come back and look at separation of variables in other coordinate systems also later in the course, but for now, the things to remember: unsteady problem, find the final steady state. The transient part is the difference between the instantaneous temperature and the final steady temperature. Transient part has homogeneous boundary conditions, and therefore, you can expand it in a series of orthogonal functions when you do a separation of variable solutions. All those orthogonal functions are all perpendicular to each other. Therefore, for the initial condition, you can find out all the coefficients in the expansions using that orthogonality condition. So, this completes our discussion of transport in a Cartesian coordinate system, and I will go on to a curvilinear coordinate system in the next lecture. I will see you then.